superstring formation?
Well, let me first thank the organizers for inviting me to participate in this meeting and give this talk. So the title of my talk is Constraints on Cosmic Superstring Formation and Their Decay Mechanism. Does this work to advance? Well, doesn't matter if it's not, I will. You know how this works?
Oh, no, it's this one.
Okay, so what I will try to do is, first of all, to examine which are the brain inflationary models which are consistent within the framework in which they have been proposed. These models, they are going to lead to the formation of cosmic superstrings, fundamental strings, one-dimensional Dirichlet brains, and their bound states. So I will examine which are the allowed decay mechanisms. And basically, I'm going to review the work which is written, is done here in collaboration with Rhiannon Wynn, who is at present postdoc at the Albert Einstein Institute, and my finishing PhD student, Spiros Sipsas. So I'm going to consider that we have extra dimensions. So we have brains of 4 dimensionality that the theory allows you to have, who are embedded in a bulk. These brains can be seen like the collection of the endpoints of open strings with Dirichlet boundary conditions, and the closed string modes, they circulate in the bulk. Now, this work was in the context, it was going to be in the context of 2B string theory, which did dual to the 2A string theory. So in 2B string theory, the BPS brains are of 4 dimensionality, let's call it P. By that I mean the brains which are going to obey half of the space-time of supersymmetric transformations, and there are charged under P+1 gauge fields. Now, non-BPS brains, which in this context are the even brains, are going to be unstable, and that you can see by the formation of tachyonic modes. Now, brain inflation. You might wonder why one would like to study brain inflation. So inflation, it is very popular because it's pretty successful in providing adiabatic fluctuations with the correct spectrum given from the CMB temperature measurements. However, one has to bear in mind that inflation is not free of problems, like how generic it is to have inflation. You have to tune the parameters to be in agreement with the data. And of course, inflation, after many years of research, it remains a paradigm in search of a theory. Now, if you go and create an inflationary model based on quantum field theory and general relativity, then what you will find is that your theory is going, the model that you are going to have is going to be controlled by the UV physics, in the sense that in your effective action, you are going to have terms which are suppressed by Planck mass. And therefore, it is reasonable to go and build a theory, inflationary model within a UV complete theory, and as such is, for instance, string theory. How can I point? Okay, yeah. Okay, so the 2 classes of inflationary models that have been studied in the context of brain cosmology is D3, D7 brain, and brain anti-brain collision, in particular D3, D bar 3. So let me very briefly review these 2 inflationary models. So D3, D7, this is a string realization of D-term type of inflation. Now what you have is you are going to have a D3 brain which is parallel along the D7 brain in the 4 non-compact dimensions. So the type of inflation you get here is dual to the D4, D6 model of inflation that you have 2 such brains to be at an angle. Now here the inflationary, the attractive potential is going to be given by the existence of this non-self-dual flux, which lies on the D7 brain, and this breaks supersymmetry and plays the role of what is known of a Yale-Leopoulos term. Now, what you are going to have is at some point the 2 brains are going to become closer than a critical distance, then the open string mode between the branes is going to develop an instability. You have a tachyon which is going to be formed, and then you have the D3 brane which is going to be dissolved on the D7 brane, and the end of inflation supersymmetry restores. However, because U1 is spontaneously broken, you are going to be left with cosmic superstrings. And the problem is that these objects, they have high tension, and therefore they will be completely spoiling the CMB measurements. So different approaches have been proposed on how you can make these objects to decay fast. For instance, if you make more complicated inflationary models where these strings will become semi-local. Now, D3, D-bar 3 inflation, this is the corresponding within string theory of the F-term inflation, which is often plugged what is called like eta problem, in the sense that you are going to have mass suppressed contributions to your inflaton potential, which means you are going to have a mass for the inflaton that's going to have contribution of the order of the Hubble, and therefore you are going to spoil slow roll inflation. Now here what you have is you have two branes, a D3 brane and a D-bar anti-brane of 3 dimensions. The D3 brane is a mobile brane, and the anti-brane is a fixed brane, and these two branes, they are placed in a particular point of the Calabi-Yau manifold. Now here the attractive potential is going to give to be given by the effect of the warping, and you are going to have an attractive force within the two branes in the same way that we had before. Supersymmetry is going to be broken. However, because the separation of the branes cannot exceed the Calabi-Yau size, that means that it's very difficult to have in a flatted geometry the first low roll parameter to be very small, which implies that you are going to have to put them in the warped geometry, and this is the known KKLMMT model. Now here you are going again, another way that you can make the slow roll parameters to be consistent is if you consider brane at angles or brane with fluxes. Here again you have at the end of the inflation to have the formation of cosmic superstrings. However, the good thing is, just because of this warped geometry, you are going to have the tension of these objects to be much smaller. For instance, let me just show you how this works. If you are going to ignore the effect of the warping, and the string tension is given by this quantity here, then you know that the CMB constraint is going to impose this constraint in the product of the Newton constant and the string tension, which by replacing with the string tension here, this is the constraint you are going to get, which means that the volume of the compactified manifold has to be at least 5 orders of magnitude greater than this quantity here. If, however, you consider the effect of the warping, then the tension is going to be redshifted by this quantity here, and then you can evade these strong constraints on the G mu. Now, so these are the two classes of brane inflationary models that can lead to the formation of cosmic superstrings. And what we would like to examine is the consistency, the theoretical consistency of these models. In other words, it has been pointed out not long ago by Komagorski and Seiberg that in order to have a consistent supergravity theory, this is only when you are going to gauge your theory, you are going to exclude the case of field-independent Fayet-Lioupoulos term, or you are going to exclude the case of compact moduli spaces. If you allow this to be in the model, then you cannot have well-defined the Ferrara-Zumino multiplet. So the question that you are going to ask is whether these brane inflationary models that I just told you are consistent with the supergravity constraints. And the problem which you have is often in these brane inflationary models, what you want to do is you would like to keep the open string degrees of freedom to be massless, whereas you want to stabilize the closed degrees of freedom, the closed string degrees of freedom, for instance, the volume of the compactification. So we address this question, and of course we address this question in the framework that we accept that whatever holds in the local supersymmetry, in other words, supergravity, is going as well to be the case for the full string theory. So then in order to see whether these two classes of models are compatible with the supergravity constraints, you have to go and study which are the details of the compactification and the moduli stabilization. So let us start with the case of the D3, D7. There you can easily see that the Fayet-Leopoulos term, it is field dependent, and this is something that you get generically in string theory models. And in order for that to remain true, what you want is the real part of the Kähler modulus to be unfixed. Or in other words, what you want is this, the real part of the S to not to be stabilized above the supersymmetry breaking scale in a consistency way. However, the supersymmetry breaking scale is nothing else than this Fayet-Leopoulos term Xi, and therefore what you get is that the scale of compactification must necessarily be stabilized above the supersymmetry breaking scale. An equivalent way of stating that is to say that in order to have a successful inflationary model, what you need is you need to stabilize the Kähler modulus above the supersymmetry breaking scale. But if you do that, then you are going to turn the Fayet-Leopoulos term to be constant and the moduli space to be compact. Is there any way out? There is always a way out. The way out is to say that if you consider quantum corrections, then the Kähler modulus is going to depend as well on the position of the deep brane. And if you do that, you can evade this constraint, but then honestly, I don't know what you mean by inflation in that case, because the bifurcation point, the Xi term, everything is going to depend, the Hubble parameter is going to depend on what is the position of the brane, which means that if you want to consider this case to evade the constraint, then you have somehow to revisit the inflationary model. What about D3, D bar 3? Well, first of all, just a side remark is that at first one can say that these conditions, these constraints from supergravity that I said before, they have been stated in the context of sigma models in a flat space, whereas the D3, D bar 3 is taking place in a de Sitter vacuum. Now, more recently, it has been shown that these conditions, they can arise here as a consistency condition for the unbroken N1 supergravity. Now, let us then question the validity of this model if it obeys the supergravity constraints. The situation is much simpler here, first of all, because we do not have a Fayet-Leopoulos term, and therefore the first constraint is not applicable here. Now, what about the second one? If you want to do compactification in string theory, having in mind an inflationary model, then what you are going to have to do is you have to stabilize your Kähler moduli at a large value above the inflaton scale, because you want the inflaton to be nearly flat. And this has been achieved in both kind of approaches to do compactification within D3, D bar 3. And the reason for which here you can fix the volume modulus below the supersymmetry breaking scale if it is because it is not tied to the scale of the volume. And therefore, the conclusion from that is that there are severe constraints that these two classes of models have to obey. It is much harder for the D3, D7 to obey this constraint, whereas for the D3, D bar 3 seems to be that is much more straightforward. So this is the first message. Now, at the end of the annihilation, so I'm going from now on concentrate on the case of branes in the warped background. So I'm going to consider D3, D bar 3 kind of inflation in order to study the allowed decay mechanism. So at the end of the collision between these two branes, then the branes are going to annihilate, and generically they are going to leave behind these cosmic superstrings, and all the energy is going to be released in these objects. And of course, one at the beginning was very, so one has to study about the cosmic superstrings, and we heard a lot from people talking before. Now, an interesting question here as well is because you have this junction that, Danny and Levon spoke before, and Anna this morning, you have this formation of this junction, and one might worry whether this network is going to freeze or not. And of course, the situation, as Danny very correctly pointed out, is much more complicated, and you have many other things to take into consideration. It's very difficult to do simulations like that and get the scaling solution, which, for instance, we found for the case of the loops and long strings for cosmic strings. However, what concerns me here, it is the situation about the observation data, in the sense that, for instance, if you combine the WMAP and the SPT, the South Pole Telescope, it was found a severe constraint on the G mu, so that you are in consistency with the data. And the question is, what is going to happen for the case of the cosmic superstrings, where you have tensions to be very big, and therefore this will be much worse. Now, if you are in the case of the warped geometry, like D3, D bar 3 in the throat, then the tension can be lowered, as I showed you before. If you want still to consider the D3, D7, then again, there are ways that I mentioned before that can somehow not evade, but somehow relax the constraints that we had. So the question is, what are the decay mechanisms of these objects, of the cosmic superstrings, if I consider their formation in a warped background, so the D3, D bar 3, for instance. So this is my metric there. And then there are three types of decay channels that you can have. You can have gravitational radiation, you can have axionic radiation, because these cosmic superstrings are going to be charged under the Rameau-Rameau and Everswortz 2 forms, and therefore you would expect that you can have particle emission. And of course, it is emission of dilators. Now, it has been pointed out in the literature, but for the case of the D strings, if you put them in a warped background, then the axionic radiation wins over the gravitational radiation. What I'm going to highlight in probably 1.5 minutes, it is that if you take the correct string compactification, then you find out that these massless zero modes are just projected out of the spectrum, and therefore there is no point to worry whether it's going to be higher than the gravitational radiation just because it does not exist there. And finally, you have as well the dilaton radiation. So, if you take the gravitational radiation, then you can easily show that if you have the cosmic superstrings in a Klebanov-Strassel throat, then you find that the emitted power spectrum in terms of the solid angle, it goes like the sum of the square of the tension of the D and F strings, which is exactly the same result that you find if you put cosmic strings with a junction. This is particularly important for the gravitational radiation from cusps, as it has been discussed before. Now, if you take, as I said, now we're going to question whether you can have this axionic radiation or not. And what you can write easily down is that if you take the case of the D strings and you want to compare the radiation in Rameau-Rameau particles with respect to the gravitational radiation, then you can find out that if you have a very small string coupling, then a negligible warping, then the gravitational waves is the dominant mechanism. If, however, you take strings in a warped geometry, then you will find that the Rameau-Rameau radiation is the dominant one. For the case of the F strings, that's what you get, and clearly, because you have this Everswortz with radiation with respect to the gravitational radiation to be proportional to GS in the cube, you find that this particle emission is going to be suppressed if you compare it with the Rameau-Rameau particle emission. However, even though you are tempted to say what could be the case for the cosmic superstrings, because if I find that the particle radiation wins over the gravitational radiation, then immediately I can have a smoking gun for the existence of cosmic superstrings if I can observe something, because there is a clear distinction between them and their gauge strings. However, if you consider the strings to be in a warped throat formed, because this everything goes for the case of the D3, D bar 3 that I said is more easily to accommodate the supergravity constraints, then what you will find that the most promising, the most consistent flux compactification which we have is the Giddings-Kasrou-Polchinski compactification, which involves an orientable projection with this kind of action, which means that the massless zero modes are out of your spectrum. And if they're out of the spectrum, there's no way to go to calculate whether they're going to be dominant or not. Now, for the case of the cosmic superstrings, the PQ strings, then you might have as well the Rameau-Rameau particle emission, because in that case, these objects are charged as well under the Rameau-Rameau form. However, one has to take into account two things. If you want to calculate what is the radiation emission, you have to take into account, first of all, which mode survived this orientable projection that I told you before, but as well, which is the correct dimensional reduction of this model. And if you go to examine that for the case of the cosmic superstrings, you will find that even though there are more and more particle emission, it is allowed. If you want to calculate it, you cannot calculate it because you do not know how the axionic wave function is going to be modulated by the watt. A very little progress has been done into that direction. So there is as well the dilaton radiation. Now the dilaton radiation, do I have half a minute? Okay, the dilaton radiation, you can calculate it. You can find out that, the mass of the dilaton in the throat, it is suppressed by this quantity that you can see here. This is A is the warp factor, and therefore the dilatons can be produced. If you take the case of cosmic strings, they have been constrained into the G mu is the linear mass density, the tension of the string, which depends on what it is, the mass of the dilaton. Now here, these constraints for the case of the cosmic superstrings are going to be weakened for two reasons. One is because the mass of the dilaton is suppressed by the warp factor, and second one, because you are going to increase the coupling between the dilaton and the matter. In the case of the cosmic string, it goes like the square of this coupling that you can see in the interaction Lagrangian. In the case of the cosmic superstrings, then what is going to be this radiation is going to depend a lot on whether they couple to matter or not. So finally, my conclusions are here with the same picture like Anna, which says that the brain inflationary models that are in the market, they have to obey the supergravity constraints, which put severe constraints in the validity of these models. The D3, D7, to my mind, has to be revisited if it is a correct model for inflation. The D3, D bar 3 passes the test with not big problem. And now, if you consider the strings in a warped background, in other words, within the D3, D bar 3 kind of inflationary model, then there is no point to go to question which radiation is going to be the dominant one, because you are going to have only gravitational radiation. Thank you. Sorry for the delay.
John is stepping up. Mike.
Just to comment while I'm on the question, I suppose. Type 2b supergravity coupled to D3 brain to D7 brain has an interesting property. It's invariant under reversing the sign of the metric.
Sorry, Gid, it reverses?
It's invariant under reversing the sign of G mu nu.
Right.
G mu nu goes to minus G mu nu.
Yeah.
Type 2b supergravity, provided you couple to 3 brains and 7 brains only, has that property. And I was hoping that that might have some cosmological significance. So my question is, will some cosmologist take a look and tell me if it does?
Well, from that analysis, my conclusion is that the D3, D7 brain inflation as it stands, it is problematic. Because you cannot have the Hubble parameter, which depends on the position of the brain. You have this is a hybrid type of inflation, and then this bifurcation that Anna showed in the picture this morning is going to depend on what is the position of your brain. And this, to my mind, is not consistent. Somehow you
had a 3 bar one.
The 3 bar is fine.
And that's okay.
The 3 bar is fine. Okay, we can talk.
Okay, next speaker is Jan.